again. Sorry about that. But I don't think for this part we needed a recording anyway. Um, uh, A, B, C, D, F, G, H, I, J, K, L. So this will be L. And yeah, now that you've done that, the next step in here, let me see. If the stat, so if an NFA state is outgoing, transition is a non-terminal, add epsilon transitions to this. Okay, we'll get to that step. So now that you've gotten this far and you've made your accept states, the next thing to do, which is an important step, is to label your accept states over here with the instruction, at least which rule they came from. So this rule over here, it came from instruction, at least like line 0 over here. So we're going to name this 0 as well. And this one, D, comes from this one. So we're going to name this 1. And this will be 2. And this will be 3. And this will be 4. So the reason we're labeling each accept state with the line number is so that is so when we later down the line, it will help us with selecting which rule it came from. So this should give you an idea. So if we're going through our accept state, if we go back to this intuitive example and we're reading this and we're going through our DFA, if we land on a certain state, that state will tell us which rule it came from. So that's why labeling them now will help us later, and we'll see how this works later down the line. Okay. Uh, okay. Next step is if a state S has an outgoing transition on a non-terminal N, add an epsilon transition from S to the starting state of the NFAs for the right-hand side of the production for N. So what that instruction is saying is that for every non-terminal, for every transition that has a non-terminal as its transition, as its transition value, what we're going to do is that we're going to add um, another transition, another epsilon transition to the segments or the NFA segments of that production row of that non-terminal. So, for example, A has an outgoing transition to B using non-terminal T, and the NFA segments that use T that are from T is 1 and 2 over here. So it's these guys. So what we're going to do is that we're going to add a non-epsilon transition to the start of the segment here. We're going to add another one over here. And we do that for every outgoing transition as well. So let me get my eraser, this pen tool. So we do that for this. This has an outgoing transition with R. So we're going to add a transition from here to there, which is an epsilon. And then another transition from here to there, which is another epsilon transition. Okay. So now that we've got this, what else are we missing? So, okay, we've done this. Now let's do this one over here. You have F with a transition of T to G. So what this is going to do, it's going to come back to over here. So it's an epsilon because E belongs to this. And we're going to have another transition of epsilon again. And that is that. And then we have I. I doesn't have any transition, so we can skip it. We have J and then K. So K has a transition of R. So this is going to come over here. It's going to be an epsilon transition. And I is also belonging to R as well, since it's rule 3. And we're just going to add another epsilon transition. And I think we've covered all of the epsilon transitions so far. I think all of the non-terminal transition. I don't think we missed anything. So yeah, now that's like the first step. Now we have a complete NFA um, with all the segments connected and with a start state, which is A because it was the first rule. It is the start rule, 0. So this is our start, and we have our accept state. So this over here is a complete NFA. So that is how you convert an CFG to an NFA of here. And that was step number 3. And make the start state production as the single start state of the combined segment. So we've already done that. It's already done where we have this start symbol over here. But if you didn't put it, you just add it there. You don't need to add the arrows there. In the textbook, I see they added them. You don't have to add them. You can add them at the end. Um, Convert the combined NFA to a DFA. So now that you have this, you have to convert it into now that you have this NFA, you have to convert it into a DFA. And how you do that, you can do in my chapter 1 video over here, just to they don't overlap. So the values. So in this video over here, I do explain how to convert your NFA into a DFA, and I explain it using a table method, this one over here. And this table method is like really useful for the SLR because um, you can convert an NFA to a DFA using this transition table. But the reason you want to convert the NFA to a DFA is to get this table. But using my method, you just get the table directly without needing to redraw the DFA as well. So you can follow that method. So I'll just paste the video over here that for those of you who want to check it out and look at that. But I'll take you through it in this session as well. So the way it works is that we're gonna have a table. A table. So let me see if I can make a table here. So, because I know I've made a table before, and this one should be it. Here we are. So the table is going to have the following values. You're gonna have your okay, you're gonna have to zoom in quite a lot. Uh, you just copy this entire thing and then just scale it down. Okay, it's good enough. Scale it down. So what you're gonna do, this table is going to have um, a column for states. Sorry about that. So a column for states, and you also have a column for the e-closure of those states. So just you can. So I like to say the states here um, present the value of x. So you can just say x instead of just like word states. But these are just the states of interest. And then you have the e-closure over here. And then after this, after your e-closure, you're going to have your transition values. And the transition values that you're going to have will be your terminal and non-terminals. So I think we have at the moment for this given grammar, we have um, we have A, C, and B as our terminals, and for our non-terminals, we have T prime, T, and R as well. So that means we're going to have five columns. So we can designate these as for our we just have not 5 columns, so this is just 6 columns. So we're just gonna add, we just resize these over here. That looks neat. Okay, I think that looks good enough. I just add plus. That might be too big, but we'll see as we go. So you're gonna have a transition for T prime. Let's just start with let's just say T prime. It's an transition for T and transition for R. Then you're gonna have A, then you have B, then you're gonna have C over here. And I'm just gonna lower this, then lower this, and then lower this. So yeah, this does take a while. Ideally, you'd like if you're doing it on paper, it'd be much faster. But yeah, since I'm on a computer, I have to fight the computer a bit, get it to work. So the first step to converting this NFA into a DFA. So the way the conversion works is that we're going to take these NFA states and we're going to and group them into DFA states. And those DFA states are going to have transitions with each other. And the grouping starts off with first you start off by selecting the start state, and then from there you perform an E closure. And the E closure is the actual group of states, the grouping of states that are related, and then we make the transitions for those states as well. So to demonstrate this, the first thing you do is you select your start state, which is A over here. So you're gonna start with A initially, and then once you have A, you're gonna perform an E closure. Let me just do this since I don't think it needs to be that big. Yeah, okay, I made it a bit too big. Yeah, I'm just resizing. Go resizing, and also while we're here, let me just yeah, can I? No, cannot. So okay, here it is. So now that we have this, well, the first thing we're gonna do is that with the start state A, we're going to find the E closure, and the E closure of of a set of states is from A, where can we go by following the epsilon transition or by doing nothing? And when you do the E closure always includes the state, at least the states themselves, because you can go from state A to state A by doing nothing or epsilon. And where else can we go? We can go from A to C. So we can go to C, and we can go from A to E as well. So we're gonna say AE, and then we keep going. From C, we can go to I. So this includes I. And then from E, we cannot go anywhere else. Oh, from C, we can go to J as well. So C can take us to I, and C can also take us to J as well. So our first state is going to be A, E, I, E, J. And then what else do we have? Um, okay, I don't see any other transition. So it's A, and then A takes us to C, and then A takes us to E and C, then C takes us to I and J, and E doesn't take us anywhere, and I doesn't take us anywhere, and J doesn't take us anywhere. So this is our first grouping of states. Right. So now that we have this group over here, what we ask ourselves is, from these states over here, where can we go, or at least which states can we go to by following these transitions over here? So now we just have to find the sets at which we have to find where we would go if we were to follow these transitions. So we're gonna look for in these states that have a transition for T prime, T, R, A, B, C. So so to start us off, we're gonna have the we're going to go to we're going to start with A. Is there like a transition for T prime? Is there a transition for T? We do have a transition for T, and that takes us to B, right? So we're gonna write down since we don't have so when you're doing this, you keep track of all the states you can go to on the next row or like the next empty row, and you populate it there. So we can go to B. And is there anywhere else we can go with a transition of T? It's nowhere else. So we're just going to have B over here by itself. And since this is B, another column I forgot to add. Let me just add a column. Is a column I forgot to add here. not there. Here, just I want to add a column. Okay, not there. Okay, let's add it. Not very usual. How do I do this? I'm trying to figure this out. Um, yeah, it can only add a column over there. Yeah, I'm trying to add a column over here. So no, let's just say I'm just going to write on the side over here. Here, I'm just gonna move this. Okay, okay, this website is now being very difficult. Okay, now I'll just move the other elements. Here. Just move it over here. Here we are. So I forgot to add another column, and a column that I should be adding is the name over here. Just write down. So we're just going to add like a rough row. So this row would be the name of the groups or the name of the states, the group of states that were interested in. So this is going to be name. So you're going to reduce this, this much. Bit more. So you're going to have this. So we're going to name these states. You can name them anything, but we're gonna what would be the best naming convention? Let's just use numbers for now. So we're gonna have like 0 over here. And you can use anything to name these states. And we're going to name this row 0. This is gonna be row 1 over here. See, I should just keep things different like so. Let me know. So the reason we're naming them is because when we finally draw our states, we don't want to have this over here, where we just have it like so. I and J. You can just have the name just be 0, and we'll just reference the table to know which steps. So in our case, we said where can we go with the transition of A, and it took us to B. And so instead of us writing B like so, we're gonna just write 1, and we'll know what that refers to as well. So yeah, that's like the convention. Hopefully that makes sense. Is everybody following along so far? Is there any questions or confusion? It's all good. Okay, cool. So, but yeah, if this is like if like my explanation is a bit confusing, in the video I do explain it a bit better. I did try putting the timestamps as well, but yeah, this is how you do it. And okay, there's an extra row over there. So this is how you do it so far. So you're just gonna do this for each transition value. So we're gonna ask ourselves, okay, where can we go by following R from these sets over here? Um, so from C we can go to D, and since we don't have a D over here, at least like an element that has a D, we're gonna have to add another row at the bottom. And okay, oh, that's weird. So we're just gonna have another row for this is going to take us to D. And is there another transition for R? Doesn't look like it. So this is just gonna be D on its own, on its own. And yeah, so and we're gonna name D. We're just gonna name this into two. The two. It's not really scalable as well. Okay, let me just create a new table. I'll just make a copy of this one. Just like for now, because I don't like this. Okay, now that works. just gonna move this over here. There you go. There you go. And we're just gonna call this name. This is just gonna be 1, 2, and 3. Perfect. And so yeah, we don't have to worry about this table anymore. And there you go. Cool. So yeah, your table would look like this. So, and a lot less hacky. Okay, now that we're here, we have 3. We're just gonna put in the name 3 over here. And now it asks us where can we transition with A from here. So E can take us to F. So since we don't have a production rule for F over here, and I mean a non-terminal for F, we're gonna have to add that over here, which is F. So we can go to F and we'll name this 4. And where can we also go? Is there not transition? So F so from F, E, okay, we can go to A. And then, yeah, I don't think there is another transition we can use, so it's just F and so on over here. And we're just gonna name this 4. Then is there a transition for B? It's J, and J can take us to K over here. So there's no K in this row, so we're just gonna add K. Now we're just gonna name this 5, and it's gonna be 5. And is there another transition for C? Doesn't look like it. Doesn't look like there's a transition with a C anywhere. So yeah, now that is our first row, and those are our first transitions over there. Um, so you just repeat this for every so that's the first step of like this is like the final step of doing the DFA. You just keep doing this and populate the table, and once you populate the table, you'll have your DFA transition table, which is what you need, which is also going to be your SLR transition table. So we'll convert the DFA transition table into an SLR transition table, and then you will be done with the SLR transition. So we're gonna keep doing this. We're gonna go from row to row, find the E closure, find the transitions, create new rows if we have to, and we just keep going until there are no more transition. No, yes, transitions that is not epsilon. I.e. So are all the X states all the nodes we can get to with epsilon transitions? You need to move to it from some transitions that is not. That is correct. Okay, I think I might be misunderstanding, but yeah, these are so the states over here, this row are the states are like at least those are the I don't know how to let me try to think of a good way to explain it. These are the states of interest. Like we start off over here with these states, and then we perform an epsilon transition, which will give us the actual grouping of states. So these states will allow us to like make the grouping over here. So this is a start. So hopefully that does that answer your question? Let me read again because all of the start X states, all the nodes we can get with no epsilon transitions. Yes, I think so. You can. Uh, okay, you might have to rephrase that. I'm not sure if I answered your question or if I'm misunderstanding. Hmm. Because from what I can explain is that the X states, these are the states of interest, or at least the states that we want to start with, and from there we do our grouping using the E closure as well. And why don't we have C in the X states? Why would we? Oh, in the X states, let's see. Oh, so why don't we have C in the X states? Why would that be C? So C, so A. Okay, the reason we don't, to explain why we don't have C, we first start off with just a single group, a single row, and that is from the start state, right? So when we want to start our grouping, we start from the start state, and then from the start state, we want to group elements that we can reach with the E closure. So we perform an E transition so we perform an E closure which will allow us to group. Um, or this is how we do the grouping of the states that we can get to without doing anything. Because the reason we do this kind of grouping is because when we convert from NFA to DFA, we want to remove the what is it called? The the non-determinism as well, and e-closures, the epsilon transition, they add that non-determinism. So to remove that, we do a grouping, and that grouping we do it using the e-closure. And the reason we don't have C here in this X state is because from this group. Yes, that is correct. Yes, that is correcto. So yeah, we start off over here with X. So when we convert from an NFA to a DFA, we do, all right, yeah, we want to remove the non-determinism so that we make it deterministic. The reason for that is time complexity because it's more deterministic as well. And we do that by this method starts off with the start symbol, with the start state, and then we group it. We're using the E closure. And this grouping will have no these are all the elements that the okay, the grouping just removes the non-determinism, and then from here we just populate the states. So you'll notice that we don't have an E closure here. So you'll see as we keep going and on and on and on and on as well. So does everybody else understand as well? So I can try to explain much betterly. Because I get and if like want to keep going, I do explain it in my this video over here, and I also written this as well. I also show you how to do it in chapter 2. Yes, they don't overlap. So I did not have the time to add the bookmarks, the timestamp, but values here do not. So in this video, I also do like show you how to do all of that as well. It's a much cleaner approach. So I forgot to add, not I didn't forget, I didn't have the time to add that as well. If you want like a better explanation, but I can explain it now if you want. If anybody else doesn't understand, or we can carry on. Cool. Awesome. So yeah, this method, you can check it out. Again, I do explain it. So there are two videos I have that explain the topic. One is in the context of SLR, and one is in chapter 1. And yeah, and now that we have this, what do we do next? C. So now that we have B, right? This B, we got it from, I feel like I'm missing something. Because we don't have, okay, since we have 2, so we can go to B. So from A to T. So this is supposed to be 2, not 1. There you go. So yeah, first mistake there. I don't think there's any other mistake. Yeah, I have to be careful about that. Okay, now B, we got B from here, from the T, because we can transition. So now what we do from here is that we get an e-closure of B, and the e-closure of B is going to include B, because um, we can um, we can get from B to B by doing nothing, and where else B does not have any epsilon closures, so B is on its own over here. It's going to be on its own. So B, as you can see, since B is on its own, we have to find the transitions, but you can tell that it does not go anywhere. There's no transitions to anywhere. So all of this is just going to be blank. So yeah, now we move on to D. D, we do an E closure of D over here. D, and it's just going to be just D because D can go to D without doing nothing, but there isn't a transition, an epsilon transition to anywhere else that we can follow. So it's just D on its own as well. And again, nothing over here. It's going to be blank. And now we have E. What else? Now we have F. And where does F take us? So F is going to start off on its own, but F has epsilon transitions. And these epsilon transitions take us where? it takes us to E. So we're gonna have F, which can take us to E and can take us to C. And then now that we're on C, C also has two epsilon transitions that take us to I as well. So we just keep following. So it's C, I. So it takes us to C, I, and J as well. And then where else can we go? So it's F, C, E, and then it just takes us to, and I think that those are all the transitions. So it's F, C, E, I, J. Well, so that's the epsilon transition of F. And now we just do the same thing. What are the transitions we can do with these? So is there a transition for T prime? No, there isn't. From these states, is there a transition for T from these states? Doesn't look like it. Let me see. T. Oh, so it's F. So F can take us to G, right? And G does not appear anywhere over here. So we're gonna add a new row. So because we're using, so we're gonna add G. So that's the row, and we're gonna name it 6. So is there another transition for T? There isn't. So okay, we just name this 6 over here. And then we're just gonna say 6. It takes us to 6. And yeah. What else? What else can we do? So is there a transition for R? Uh, doesn't. But the pause is that there's no shortcut to say. Yeah, there is no shortcut. It's like with this, I can. This is the best method. This is the fastest in terms of like doing the SLR. But once you get over this hurdle, it's the rest becomes much easier. So the most difficult thing about SLR is just converting this NFA into a DFA. So knowing how to properly convert the NFA to a DFA is that. And I think I do kind of mention how to do it fast. The only way to do it fast is through practice and also making
Written.
sure that you don't make a mistake as well. But yeah, it's very frustrating. Well, um, yeah, 6. I don't think so. R. I don't think R. R. Yeah, I don't think there's another transition for R. And A. Is there a transition for A? And A takes us to F. So now from F, E, so we have E here, and E takes us to F using the transition A, right? So we don't have to add another row for F in this case because F is already here. We already have it. So what we do here is just write F for that, since we don't have to write that. And well, do we have another transition? For B, yeah, we have B, J. So that means J of the transition of B, but something feels wrong. Okay, so of B, we can go number 5, K. Hmm. Okay, okay, yeah. So with J, we have a transition B. Like I'm missing something here. Yeah, I think I wrote it in the wrong place. Yeah, I wrote the 4 in the wrong place. Okay. Okay. So yeah, with B, now with a transition for B, um, in this, we can go from J to K. And is there another one, another transition? Yeah, there isn't another transition for B. So it takes us to K. We don't have to add another row for K because we already did over here. So we're just going to write 5 like that. So is there a transition for C? No, there is not. No, there is not. Yeah, no, there is not. And the rest is empty. Yeah, that's this. And now we keep going, keep the flow going. So K, let's find the E closure of K. K, we're gonna have K, then we're gonna have I, and then we're gonna have J. So is this right? So K takes us to I, and K takes us to J. And there isn't any other transition. So this is just that. So now that you have this, ask yourselves the same thing. Is there any transition? As you can tell from these three, the only transition we have is for B and R. So for B, so we don't have T prime, we don't have T, and we have R, and R takes us to L over here. There's no L over here. And what we're gonna do is just add another one. L. Also, something to note is that notice that I'm not just writing just L over here. The reason for that is because it's a set. So there could be more than one state. So one state could take us to R. It can have a transition for R, and another one could have a transition for R. And in that case, if it was like that, we'd have something like this, like A K L K, if that was the case. So there could be more than one. And and notice that there's a K here and there's a K there. Why are these the same? They're not the same because these contain different sets of like things. They're different sets. So yeah, but that's just like a case. I'm not sure if that case will show up here. But yeah. So yeah, you have L, and then yeah, I'm gonna name this 7, and then this transition happens here, where it's just going to be 7. And then have A, B, and C. So we just have the B, which takes us to K, and we already have K, which is just going to be 5. And then from 5, do you have, for like, yeah, I keep making the mistake. It's just that. So K, J takes us to K. And yeah, that's 5. And there's no C. So yeah, that's that. And we can look at G for now. So we move on to the next row. So G only has a transition for C. So when we try to do epsilon for G, it's just going to be just G because there's no epsilon transitions out of this. And G has only a transition for C. And the C takes us to H. And there's no H here. So we're going to add a new row for H. It's just going to be H. It's just going to be 8. And yeah, that's it. And then, so we're just going to say C takes us to 8. So, and yeah, yeah. What else do we do here? So now we're going from C to H. Yeah, I don't think there's anything else for us to do. So we move on to the next one. We have L. We do epsilon transition for L. It's just going to be L. And there's nothing for L over here because there's no transitions. And H. H, when we do epsilon transition for H, it's just H. Nothing else. And I think that's it. That's the well, since we don't have any more rows to process or do, this is our final table, our DFA. And you could draw this DFA, but you don't have to. This table is all you need to complete the question, at least to answer the question. So, any questions so far about this process of converting an NFA to a DFA? No, I'm assuming no questions. Yeah, it's a long process, but it's the best way. You'll see why. Again, I do have a chapter 1 video explaining the method in great detail, these using actual examples, and then you can use this exact same method for this one. And the nice thing about this one is that here, over here, this is the first step of your SLR table or pause table, it's called. So now we've already done, so we've done this step, done that step, and we've done this step over here. Then make this, and we've converted that. Now we have. So build a table cross-indexed by the DFA states and grammar and terminals, including this and non-terminals. Add shift actions for this, including the dollar sign terminal. Let's see. Do you have the dollar sign here? I don't think we had the dollar sign anyway. Okay, I think we have the dollar sign here. Okay. So they wanted a dollar sign transition, even though we don't have a dollar sign anywhere, I think. I don't think we have a transition for a dollar sign in. neither does that, but we'll just have it over here since it says so. So it says create a cross table, and you've already done it like this. So this is the cross table, but it's also mentioning something called add the shift actions for the transitions and go actions for the on non-terminals as well. So what are shift actions and what are go actions, or what are actions in general? So actions in the case of SLR are the steps that you take when like generating your tree. For example, let's go back to when we were doing this over here. So the uh, us going from here to here is shifting, where we're shifting from this token to that token. That's a shift right there. And the process of like popping, like making this transition over here where we go up, that is a go step. That is just going. So we tell our processor, the algorithm that we have will identify these actions as go and shift. There's also another one called stop. It's either stop or accept. I think it's accept, where when you reach the top, the action is accept, and that's when you know that you're done. And another action, yeah. Uh, Go is the same name as reduce. I think so. Go and reduce. Yes, yes, yes. Because I know with this, you're gonna have this rule, and you're gonna reduce them into a single rule. And the shift is when you go from one token to another token as well. So yeah, I think they're the same thing. I'd say they're the same thing as well. But I'd have to let me double check to be on the safe side. So let me see actions. I think they should be separate. There's reduce. There you go. Because there's a section where it explains each rule better. Actions. Okay, just say reduce. Uh, reduce. So you can have four actions. There's go, and then there's reduce, and then there's a shift, and then just accept. And you have to populate those on the table so that you know what to do. So go and reduce should be separate rules. I think they're not the same. Misspoke there. Okay, this book is not explaining that. Let's go to chapter 2. Okay, not this one. Okay. LR, SLR. There we go. So over here is when it performs the shift, reduce, and go actions. So this is the algorithm. So okay, I'm just gonna copy this over here, this algorithm. We'll get to it later. I'll explain it later what it's about. But you're going to have your shift S, your reduce P, and accept an error. So whether reduce and go, are they the same? Huh. This is a first for me. R. I think go and reduce could be the same, but I don't remember exactly. Um, but we'll see. I think so. I'd like to say so, but I'm not too sure at the moment. So we'll just follow the book for now, if that's okay. At least like this. Oh my, what the hell did I? Okay, that's bad. That's there you go. So it could be different because I know go actions higher. Let me look at the second edition of the textbook out of curiosity. Just quick sneak. Let me just look at the video because I know I used the second edition while explaining over here. Yeah, okay, we have go N and then reduce P, accept, and shift N. Okay, so yeah, there we go. So I was looking for this exact bit over here and pausing. I completed. Okay, here we go. So it's on page 99 of the textbook. So Shift N, push the current input symbol, and then state N on the stack and read the next input symbol. This corresponds to the transition on the terminal. So let me just copy this and try to explain it. So yeah, they're different. So reduce and go are different. Oops. So we'll just add it here. So try to explain it in the context of this. So Shift N, see, cool. Position and reduce is what you could replace with instead of that. No, it's not correct. Yeah, it's as he says. So the Shift N, push the current symbol in the current input symbol, and then state N on the stack and read the next input symbol. This corresponds to a transition on terminal. So this is the same as just like picking, okay, you're done with this, move on to the next state as well. So the way I'm explaining it is like high level, like how you would like see it if you were to like visualize it. But we are making use of a stack and the DFA just to like understand. So go N, push the non-terminal indicated by the column, and then state N on the stack. This corresponds to a transition on a non-terminal, and reduce with the production numbered P pop symbols interleaved, corresponding right-hand side of the production of the stack. This is always by a go action on the left-hand side and non using the DFA that is found after popping the right-hand side of the stack. Pausing has completed and a syntax error has occurred. So okay, these are the actions. The ones I can explain right now is the shift. At least I know that the shift works like this, and the reduce is if you're going upwards, where you're just like reducing this rule and this rule into into like a small into a non-terminal as well. Cannot the accept is when you reach like the top of the tree and you're done, and an error is when you try to do an action but something went wrong and you just throw an error. At least like something was not supposed to happen. So on your table, your information, if you read a table and there's like an error or like there's nothing there, then there's usually an error. You throw an error. So okay, hopefully that kind of makes sense, but this would make more sense if you look alongside it with the cool, thank you. So okay, so this what's the algorithm? So this will make a lot more sense if you look at this algorithm over here. So this algorithm will make use of the table, this table over here, to perform the actions, at least to grow our tree, and we'll do these actions. And to make this algorithm work, we have to populate our table with these actions. Uh, what is a connection here between the two of them? So we have to populate our table with these actions. And to do that, it's very simple. It's very simple. So what we do, right, is um, build a table cross-indexed by DFA states and grammar symbols, terminals, including the dollar sign and non-terminal. So we've already done that. And then add shift actions for transitions on terminals and go actions for transitions on non-terminals. So for every terminal, we're going to add a shift in front of it. So that it's in this format, shift N. So we're gonna go into our terminals. So these over here are our terminals, at least this side of the table is. And what we're gonna do is say shift 4, and we're going to add a shift over here. And you don't have to write the full. So if you don't want to write the full word shift, you can just write S just to abbreviate it as well. It means the same thing. You just write S and over here S and over here S. And remember, the reason I'm doing this on this side is because everything on this side is a terminal. So now I have S and then you can have S. So there you are. And then you have these over here. The terminals, the rule says go actions for transitions on non-terminals. So we're gonna have go, but if you don't want to write the full word go, you can just write G and then G and then now G and now G as well. And like that. And let's see. So now you've added all of your shift actions and your go actions, and now we're left with these three over here. So the next one to do is reduce P. So how do we add reduce P? So to do reduce P, we have to calculate the follow set, the follow set for each non-terminal. For this purpose, we add one more production for one more start production, which is S prime prime produce S prime dollar sign. So that means to get our reduce right, we have to the first step to do that is to get our follow set. And to get the follow set, we have to take our current production rule in our CFG and we have to add another rule, which is this one. In our case, it's just going to be T prime prime produces T prime dollar sign. And now we have to calculate the follow set of each production rule. And doing the follow set is very simple. Just do this. So let me just increase it. So the end of video, I do have my video on chapter one over here. Chapter one video. I do explain
Written
not the chapter one
this as
video,
well.
the chapter two video. What did you? They don't overlap. So in chapter two, I do show you like a simple way of like getting the follow set somewhere over here where I just use. Okay, there you go. Yeah, it's the first 15 minutes of the video. I explain how to get how to quickly get the follow set of anything as well. It is in the visual way. I do explain in a visual way how to get the follow set as well. So the way it works is you just look for each non-terminal. Let's want to find the follow of t prime prime. We just have to look for which one on the right hand side is t prime prime reference, and we don't see it anywhere. So we're just gonna have it empty. Then you're gonna find the follow of t prime, and on the right hand side, where is t prime followed? It's on this rule over here. And t prime is followed by what? It's followed by the dollar sign. So you're just gonna have the dollar sign over here, and then you just continue for the rest. So what is the follow of t? The follow of t. We look on the right hand side. Where do we see t? We see t uh, over here. And let me just get an eraser and the pen. So we see t over here, and we see t over there. And in our case, we're like, what follows t? Nothing follows t over here. But so that means whatever follows t is going to be whatever follows t prime. Because at least in this case, in this scenario, since there's nothing that comes after this, what comes after t will be whatever comes after t prime. And in this case, what comes after t prime or what follows t prime? T prime it's going to be the dollar sign as well. So you're just gonna have your dollar sign here. And over here, this T over here is also followed by the letter C as well. And yeah, that is how you get the follow of T. And you're gonna have the follow of R as well. And the follow of R. So this R is just empty. So where is it referenced? It's referenced. Let me get the eraser as well. So R is referenced. So it's over here. It's over here. So here, since here nothing follows T, it becomes that whatever follows R, whatever follows R is whatever follows T, and it just so happens to be this over here. So R is going to have those values. So to have dollar sign is going to have C, and are we done? So here R is followed by nothing. So that means whatever follows R is whatever follows R, and in this case, it's so in this situation, if like you have R and you're like whatever follows R is whatever follows R, it's gonna be nothing as well. So uh, you're gonna skip this one, so you'll just end up with this as a final answer. So that's how you get the follow set as well. I do explain like in a visual way how this like rule works and like how to find the first and follow the nullable, at least what it means in this video over here. And like so yeah, I do explain the concepts as well. So yeah, that is that. Uh, with this, is there any question on how to find the follow? So it's fairly quick and simple in my opinion. I'm assuming everybody's good. So, all right. Now that we found the follow set, we can now use this to find the reduce rules. So we can add the reduce rules. So the reduce will help us like decide which production rule to reduce to as well. So let's see. So we take this, right? And see, when a DFA state contains an accepting NFA state marked with production number P, um, where the left-hand side non-terminal for P is N, find find the symbols and follow N and add reduce P action in the DFA state at all these. If P is zero, then an accept action is that. I'm gonna have to read that again. That's very confusing. Mm-hmm. Left side, non-terminal. Okay, so I believe here we're gonna have to look at over here, and we're going to look for production rules that are accept states. Well, and those will be the rules. So reduce P will be the product CFG rule that is an accept state. So this P will be the number, this number over here that we labeled with. So we need to find out where will we add reduce 0, reduce 1, and reduce 2, and reduce 3, and reduce 4. And again, to summarize, reducing is like when you have your production, your tokens, or your other roles, you reduce. And if you keep at least reducing is the main mechanic that allows us to go from the tokens and takes us all the way up until we reduce to the start rule over here. Let's see. Let's see. To do this, the first thing you do is you have to find um, the production rules. And this you have to look at the e-closures over here, the groupings. And from these groupings, you look for the accept states. For example, accept state B. So B is over here. So that means you have to add reduce 0 in one of these columns. In which column do we add the reduce 0 in? And this tells us which column to add the reduce at. So in the case of B, B is which rule again? B is which number? B is 0, and 0 is T prime. So since it's T prime, we're going to look at this over here, and we're going to add it at this column. So reduce 0, we add it at the $ column. So we're going to add reduce 0 over here. So does that make sense how I got to that? Like how I got to this point? Um, if anyone's confused, you can let me know. So, but I'll do it again with the other rule with D. So we're going to go through over here and look for the production for the sets, the e-closures that have D in them. So this has a D. That means we're going to have to add reduce 1 over here and at one of these columns. And D does not appear anywhere else. So in D1, rule number 1 is T. So this is T. So let me just number this again: 0, 1, 2, 3, and 4. So we're going to reduce to this rule. So we're going to add, so the non-terminal for this rule is t. So that means we're going to look at this one over here, and we're going to add reduce one to these columns over here. So we're going to add reduce one to dollar sign and C. So we're going to have reduce one over here and reduce one over here. And we follow the same thing. We're going to have, let's see, what's next? H. We're going to look for the rules that have H in them. So this has H, so we're going to have to add reduce 2. Is it anywhere else? No. And reduce 2, the rule for 2 is T. So that means we're going to add reduce T in dollar sign and C. So reduce 2 is going to be here. So reduce 2 and reduce 2, like that. And yeah, we keep doing this for the other rules. We have 3. We look for it. We have the rule 3 for I. And where is I? So I is here. That means we have to add. Where is the 0 and 1 coming from? Just the order of the reduce, or is it correct? So so these rules, they correlate. So remember at the beginning, we added these numbers. So we labeled 0 each except state according to the we labeled each except state according to the production rule they come from. So each segment, so this one came from rule number 0 over here, and this one came from rule number 2, rule number 1, and this one came from rule number 2, and then 3, and then 4. And for each there, we made the last state of each one the except state, and then we labeled each except state according to the production rule. So this is production rule 4, 3, 2, and 1, and 0. And yes, the reason we do this is to know when to reduce. This helps us decide. Again, this also helps us decide which rule do we. So remember when I was explaining at the beginning, I was like, we read A and we know it's gonna be rule number 0 or 1 or 2. So that's the reason we labeled that. And how we use that is like this as well. So we have reduce 2, and then reduce 2. So here we're going to add I. I is for rule number 3. Rule number 3 is this one, R. So we're gonna look for where R is. So it's gonna be R3, reduce 3, because there's an I over here, and then there's an I here. So we're gonna add a reduce 3 here. So that means in one of these columns, we're going to add reduce 3. And which column? Since rule number 3 is R, we're going to add it into this column and that column as well. So it's going to be reduce 3 over here, and reduce 3, and reduce 3, and reduce 3, like that. So yeah, that's how you add that. Then the last rule, L, for rule number 4. Rule number 4 is R produce BR, which is this one. We look for everywhere there's an L. It's just here, just R4. Is L anywhere else? Doesn't look like it. So where do we add 4? Since rule 4 is this dollar sign, so it's gonna be reduce 4 and reduce 4. And that's how you do it. So yeah, I'm gonna erase this bit over here. Okay, it's a very bad eraser. So yeah, this is just for us, like, to reference. Yeah, that's how you do it. That's how you add the reduce rules, and that's how you do it. So you first calculate the follow set. Then at the beginning, when you made your NFA state, you labeled the except states, and that's when we use them now. So that's how you add your reduce. So any questions so far on how to get shift, go, and reduce? Uh, no confusion, nothing like that. Okay, so it's cool. Again, I go through this process again in the video if you want to. Okay, this is just for like producing, but I do have a video again explaining that process. And let's see. Um, so now we've added this. How do we add the except state? So for the except state, remember, since here we're gonna keep reducing our way up or like keep going our way up, eventually we're going to reduce to like a point where we need to stop. When do we stop? We stop when we get to the first production rule or the start production rule, and that's when we know to stop. So if we reduce to this rule, because at the beginning we'll be reducing to rule number 4, 3, 2, 3, 3, 4, 4, 4, 4, 3. But when we get to reduce 0, that's when we know we have to accept we're done. So because of that, because of like if we reduce, we eventually like reach the top. Um, it's telling us that add an accept action instead of reduce p action if p equals to 0. The reason it says p equals to because that's the start. But any rule could be the start. Like you choose which one at the beginning, which one is the start rule in this, but it's almost always the rule you just added the t prime equals to t, which is this one over here. It's almost always that. And yeah, so it doesn't have to be 0. It's whatever rule. It is the start rule. It's the start rule. And in our case, it's S prime produce S, which is always 0. So because of that, wherever we reduce to 0, we accept. And in this case, it's over here. So we just change this into an accept. So we just write this into as an accept. But in most cases, you don't have to write the full thing. You can just write ACC for accept. And that is how you add your accept as well. And this usually indicates that your pausing has completed. And yeah, so that's how you do it. Now, what about the error? How do you know something went wrong? A syntax error has been detected. This happens when no shift, accept, or reduce action for the input. The error already is there, so the blank tables, at least the blank cells, those will be the error. So if we're going through it, if we're going through the DFA and we somehow end up here for some reason, we don't know what action to do, it's usually an indication that there was a syntax error. I'll explain what this means, like to end up here. And so all you need to know is that all the other blank cells are just those would usually cause an error. And another thing is that if you're making your table, and let's say that you have a reduce 4 over here, and then you let's say you have like another rule, another except state, and it also adds reduce 5. If you have this, like where one cell has more than one action, that's a clash. And it usually means that something went wrong. And it usually means that the language or the CFG you picked is not compatible with SLR. So that's a sign that your SLR is not like your SLR does not support the grammar if there's like a clash of rules or actions as well. So that is that. So if you so those are the two things. So that's the error, and that's the at least how to know if there was a mistake or your grammar is not correct. So that is how you produce your SLR pause table. And usually an exam question would ask you to produce this, and the longest part of this is, of course, converting from NFA to DFA. But if you do it effectively, if you use the method I show you over here, you'll be able to at least skip the hassle and just get the right table and such. And once you produce the table, you just populate the actions. And yeah, that's how you get the table. But now that we have the table, what can we do with it? How can we use it to generate a syntax tree? That's very simple. You make use of an algorithm that can read the table. So this is the SLR table. This is the algorithm for SLR parsing, where you start off with an empty stack and you initially push state 0 and the stack into the stack. You push 0 into the stack, and then you read your input, which is usually your tokens, and then you loop through the table. So this table over here is referencing our table over here. So let me just move it and just copy it to over here. Okay, very large. Uh, just expand a bit more. All right, here we are. So now you have read inputs, and so read input just reads like the next input, so it's gonna read each token one by one, and then you're going to this reads the next input. Then you have your loop, and then you're gonna go through the case table, the top of the stack. So you're gonna look at what the value of like what's at the top of the stack, what's at the top. It could be like you could have like one, two. The stack usually just has like the states. So you're gonna look at what's at the top, and then you're gonna get your input. So you're going to compare the top of the stack with your current input. Like so you're gonna read this, and then you're gonna look this, and based on that, you're going to know, and that so you're going to look at this over here, the state, and then you're going to look at the value, and what how the table is going to work is that it's going to look at what state you're looking at. Let's say this is state 3, so it's going to look at this over here, and it's also going to look at the current value, and the value will tell you what action to perform. So, for example, the top of the stack could say 3, which correlates to this, and so it starts off with a 0. Let's start off with like the 0 over here, and then it's going to look at the start. So you're going to table 0. Okay, mine doesn't start with 0, so in our case, we just mine starts with 1, but starting with 0 over here. So I made a mistake. You're supposed to start with a 0 as well, but that doesn't really matter too much. So in this case, you just put in 0. It's just the first step, if that makes sense. So once you iterate through it, you're just gonna look at each block. So you're gonna look at a cell. So if a cell lands over here at S4, because the next input was A and the top of the stack was 4, we're gonna have shift 4. And this will correlate to here because it will be shift 4. Uh, shift 4. And since it's shift 4, we're going to push the input onto the stack. And the input could be, let's see, read input. I think that's the current value. Then we're gonna push S onto the stack, and S is the number 4 over here. Uh, cool. And then we're gonna read the next input of the table. So we're gonna push that on top of the stack as well. Hmm. Very confusing. Why is it saying input into the stack? Oh yeah. Is it? It's a shift 4. Mm, okay, I feel like I'm misunderstanding something, but you get the idea of like how you're supposed to at least read through this. And then you also have reduce 4, which is the same thing. So if you're reading your shift, your top of your stack and your input, you might and you land on reduce 3, like reduce 3, you're gonna get n equals to the left hand side of the production rule, and the left hand side of the production rule is mm, the production rule is usually this, the t, the non-terminal, production p, and the number of symbols on the right hand side of p. So if we have t, for example, if the left hand side is t, the right hand side would have one, two, three elements over here, which is what's going to be this. So in the example that let's say our production rule is this, n could be t, and this could be the number 3, and then you're going to pop 2 times our elements from the stack, let go s equals to table, the top of the stack, n, push N onto the stack and S onto the stack. Terminate with success. Okay, if you so okay, this you can all try to read it, understand it. Currently like not following it is trying, but the idea does take your time. I would suggest going through this to see like how it works. But that's like the main idea. If you land on an accept, you're done, you're finished, and then report error. And if you follow this algorithm, you will usually end up with a table like this over here. So it will usually help take you to, you usually end up with something like this, where you have your stack over here, and then you'd have your input, and then you'd have your input, you would pop it, you would shift it, and you would, for each row, you would performing a different action. So you're going to start off over here, and then you're going to reference the table, which action you're going to do. And then as you move on, you'll be doing those actions. So here, the action is shift three, shift three, shift four, shift four, shift four, until it reaches the accept state. So yeah, that's how you do SLR pausing and how to produce the table and what to follow. In an exam situation, I imagine it'd be useful to have this algorithm written down, but the rest of the and this algorithm and this step written down. And if the explanation, if you want like another explanation, is a much more structured one, you can follow again this video over here where I explain the same thing, the same
Takes us
process,
to and
same process, at least how to do all of this as well. And yeah, that is how to do SLR pausing. The types of question you might get asked is to actually chapter two. It's always the chapter two are the most straightforward. That get the most straightforward questions where make your LL1 pause table or find a mistake in the syntax tree, prove ambiguity or such, or make use of the algorithms. Hopefully, did that make sense, everybody? Hopefully that clears it up. If it doesn't, like, feel free to let me know. And yeah, cool. Okay, do you guys want to move on to the next chapter, or are there still questions on this one? I'm assuming everybody's good. That so I don't think I'll cover LL1, but I do cover LL1 in the video over here. It's not time stamped over here very properly, but there is content here for you to like. I go through LL1 and I go through SLR as well, so you can watch that. So which basically covers the whole chapter. So I think we can move on to chapter. Okay, chapter four, chapter four, chapter 4, 5. They're practically the same thing, but we can do chapter. Which one do you guys feel like doing? Chapter 4, 5, or 8? So I have a video on chapter 8 in case you guys like
now
also
it
want that.
says attempt.
I do explain, take you through a question for that. So, but I can also go through it in this session. Um, yeah. Okay. Like, just waiting for people to finish typing so that I can carry on. Okay. So chapter 5 because there's a video for chapter 8. 4 and 5 maybe because the video is useful. Yeah. So chapter 8 video is over here. It covers everything from start to finish. Um, I think it's covers enough to get you started, space, all of that. So we'll do 4 and 5. Since I don't have videos on those as well. Chapter one, I have a video on that. I have a video on chapter one. So we can do four and five. And if we have time, we can do another chapter as well. If that's cool with everybody. Cool. And yeah, but if you have like a different question for everything, a Jeep, I don't know what that means. I don't know internet slang. um, yes, like cool. Is that like a different language? Just curious. Let's see. Chapter three. I usually don't have much to say about chapter three. It's a simple table. It's only useful for the practical sessions, at least if you're working on a project. So let's do like a verbal thumbs up, I guess. Okay, I'll keep that in mind. Hopefully that doesn't like get me fired at work or something like that. So okay, chapter four. Okay, chapter four. We're gonna do chapter four and chapter five. In my opinion, they're not too difficult. If you understand chapter six, they're practically the same thing, but again, the goal is different. Like what you're still traversing, and the way the questions are asked are very similar as well. So you have chapter four, which is interpretation, and chapter five, which is type checking as well. So at this stage, to summarize, you've done your lexical analysis, and then you've generated your syntax tree over here using, let's say, SLR parsing or whatever, really. Well, you have your SLR table over here. So you have your graph. Let me just expand it so that it's way bigger. So you're gonna have your graph over here. You're gonna use SLR parsing to generate a tree, and your tree will look like this. And when the tree is like that, now you want to decide what do I want to do. And in chapter four, this chapter is all about interpretation. And the whole point of interpretation is evaluation, where you've now paused your code and now you want to get an output out of it. You want to get a result. You want it to evaluate. And an example of this that I like to refer to is syntax tree math. It's just like a math equation. So here's an example where you would want an interpretation of here. So your syntax tree could look like this. I believe this could be an abstract syntax tree, but they're all the same. Am I wrong? Let me just double check an abstract syntax tree. Okay, so they have the abstract syntax tree, because okay, I'd have to remember exactly which one, because I know there's a tree where, okay, it is an abstract syntax tree where it usually does not have the non-terminals or it's just the values. But so yeah, this is an example. So an example of interpretation is that your code would look like this. So let's say this is your code, right? You would tokenize it like so. So you tokenize each value, and then from here you would apply an algorithm to parse this into a tree. So one way of doing that, at least a tree would look like this, would come up like this. So it could be an LL1 or an SLR syntax tree, you'd be able to tell, or you could use any other algorithm. The whole point is now that you have a tree. Now that you have this tree over here, you want to get a result from it. And one way of doing that is that you can think of each one of these as a node. And this is a node over here, and this is a node over there, another node over here. And let's say that these are its children. So what you would do is that since this is the plus operator, you know that I'm going to add the left-hand side to the right-hand side. So to do that, you're going to look at this node and you're like, give me your result, give me your value. But this one is a multiplication node. And to get the value of this, it has to multiply its left-hand side with its right-hand side. So so it says, give me your value. And since this is a number, so this node gives a number, it's going to return 2. And then it says, give me your value. It's going to return 7. And inside the logic over here, it will multiply these two together, and we're going to get 14. And then the 14 gets returned to this plus over here. So now it has the 14. And then the node is going to be like, okay, the right-hand side, now give me your value. It's going to return 3. And it's going to evaluate 14 plus 3 is 17, to which the final result will be 17. So the head of the node will have the value 17. So the value just gets populated upwards. And it's the same idea here. Left hand side, give me a value, gets a 2, give me a value, it gets nothing because it's still this one has to evaluate itself. Give me a value, it's gonna be 7, it's gonna be 3, adds them together, it returns a 10, then uh, multiplies these two together because it's a multiplication, so it's going to be 2 times this, it's going to be 20. So the final result here will be 20. And again, the final result is always at the head of the node as well. So that's how it usually works. So it's a traversal problem. So you're just doing a def first traversal and you're just getting the result and outputting it. And that's interpretation in a nutshell. Um, but this time we do it using programming languages. And an example of that is Python. And Python does that where you can just open up a terminal. You just open up a terminal real quickly just to demonstrate. I think I should have Python installed. What happened? Okay, something happened there. So Python, when you give it a result like this, like 2 times 7 plus 3, it will give you a final result. And the way Python does this is that it does the exact same thing. It lexes each one and it lexes each one and then gets a syntax tree for this piece of code and then it evaluates it as well. So it can also do that with like print um, 2 times 7 plus 3 as well. And again, this might seem a bit confusing. I should have done something different, but the way this works is that the syntax tree, we just have another one over here, a print statement. So this is like, okay, I'm going to print my child. So it prints its child and the child has a value of 17 and it does that. So that's how it works. So how does it actually do this? The textbook again makes use of a table. And first, it describes the language for interpretation. So this is the example language for interpretation. So we're going to interpret this language over here. So it gives you this language. So this is the programming language that we like write our code in. So we can give it something like this where we can say, let X, I'm just looking at this rule over here. I'm just like making stuff up. Let X, mm, just want something simple to work with, like an addition. Okay. Mm, okay, now let's just say, let's just do 2 times 7 plus 3. Uh, the same example over here. 2 times 7 plus 3. And if we were to get the syntax tree for this one, it would like probably be like exp and let's see exp. So we're gonna do this. I'm just gonna draw. Okay, just spot. It's just a segment, just to demonstrate. Just make this thick, and also I want it to be free flowing as well. Uh, so we're gonna do expression. Okay, there you go. Expression. Um, okay, there's no multiplication over here. The textbook does provide an example thing to evaluate. Evaluate. Even the chapter is very short, like because it's not much going on. Small example language. See. Evaluating call. Okay, it's not giving me an example language, but is there an exercise we could do? Okay, it's also not giving me an exercise as well. I could have sworn there was an exercise we could do, but we'll just so the tables are very simple, are very similar to the ones in chapter 6, and where you'd have a function, a table for each non-terminal. For example, you'd have a table for this over here. So you'd have a table for this over here, and then you'd have a table for that. And we're missing one more table. And we're missing another table. There we go, this one. Okay, here we go. Okay, so we look at our production rule. We'd have a table for this one to evaluate this one, a table for this one, and a table for this one, and a table for this one, and this one, and this one as well. So as you can see, it's the same as chapter 6. It's exactly the same. The difference is that we are returning a value instead of like producing new code. So this over here is is for this. So for this, we make a whole table where we have eval. So we eval the expression. It takes in an expression and it takes in a v table. So the v table, the syntax, I think the variable table, this contains uh, the values. So this v table is different from chapter 6 because the v table was a simple table. This v table has actual value where you'd have it would look something like this where you'd have x equals to then you just use like this kind of table. It's a very bad table structure. So you have x and y and z, and then you'd have actual values like 12 or 15 or negative or just even a string value like hello as well. So it has actual values. And the reason this has values is so that we can like process, like get the value as you see over here. So we get the value, we pass in num and we get the value, and then we do some sort of operation like addition or such, rather than um, the value table from translation where you're translating, where x would be translated to v0 and y would be translated to v1 and z would be translated to v2. So hopefully that makes sense to you guys. So here we're dealing with, so this v table has this, and the f table, I'm not too sure. I think this might, let's see, I'm guessing the f table are all the functions as well. I don't remember if the F table does anything in particular, but we'll see. F table. I'm guessing the F table is also the functions, and the functions you can pass in values and do function calls. I'm guessing, but I'm not too sure if I remember that. Evaluating a function call. So here we do a function call type. Okay, these are the type IDs. So we do a function call, we bind, so vtable, we get the vtable, evaluate. If v1 is of type t0, then v1 as well. So this is just initializing, at least it's starting something. It doesn't really make that much. At least I think this is just like setting up the v table and the f table. The f table, we're missing one more table over here, which is this one of them. There you go. So here you are. So these are all the tables for interpretation. So the way this would work is that you would get your input, you would pass it in, you would start off with our run program over here. So let's say you were given like x plus y, something like this with the following v table. Normally you can go through all of this where you start off. Is the only way they can ask us a question is to just use the tables. That is correct. So chapter 4, you could either make the table yourself or use them. So it's the same thing with chapter like 4, 5, and 6. They're all the same thing. They practically the same thing. The difference being is like what the tables do, or at least what the goal is. And with chapter 4, it's interpretation. So your end goal is to get a result, as we've seen like over here. But compare it to chapter 5, which does type checking, where you would check if like the like for you check for something like this. See, for chapter 5, I think there was a question over here that I did. Uh, the chapter 5 would look like this, where you'd have your syntax tree, and instead of getting a result, you're getting whether the program is correct or not. Is there correctness, or is it like type safe? And when you evaluate it, you might get something like this as well, where where you get the types and you're checking the types, and in the end you're gonna say whether the whole tree is wrong or not. An example of a wrong table is that instead of here being 7, let's say we just had a string that said 7. And this one, instead of returning a result saying 2 or what, this would say this is correct. And here it would say the value here is correct. But when we try to multiply them, you cannot multiply a number in a string. So this would not be correct. And it would bubble up like that. And it follows the same technique. So if you know chapter 6, you can reasonably do chapter 4 and 5, because chapter 5 is doing the same thing. They're all doing their first traversal. It's just what are you trying to get? What are you trying to do as well? So chapter 5 is exactly like that as well. The only difference is the v table, and because they need the v table require different purposes, and the v table in chapter 5 would I imagine would have the values, would have the types instead of like actual values. It might have values, but it could also have the types where it just says this is a string, or uh, this is an int. So instead of like return value, it's just gonna say this is an int. Um, the v table look up, get the ID, is was the value declared. So over here, if we have an ID in chapter 5, we see was the ID does the ID exist in our v table instead. But if you look at chapter 4, it's more, and you look at the same thing over here, it says what is the value, like get me the value, and if the value does exist, return it, else throw an error. But here it says if the value does exist, what is the type? The type exists, just return it. And over here, and in chapter 6, in chapter 6, the same thing would just tell you if um it would just tell you what that variable is. At least it would do a translation instead. So does that make sense? Like, does it make like, and he's like, am I making sense with the way I'm like explaining? Because to me, these chapters are all the same. Then they would all be explained the same way. The difference is like their goal, like what they're doing. So here, doing a lookup and get the v table, and then the lookup in the v table would be if we have x and then 4. So does that make sense, everybody? Like, So that's the only difference. It's still the same. Like there's no real difference. If you go through them, you'll notice that they're exactly the same. And um, when I teach like these three chapters, again, this is why I say they're all just traversal. Like, what is the goal? Here we're just evaluating. Here we're checking correctness. Here we're just translating as well. And that's like if you go through the codes, and I do have a video. Again, I keep referring back to the videos, but I have a video for this that takes you through how to read the tables. Like, it's like the first thing, yeah, it was the first video I ever made, and it explains the exact process, how to use the table, and it's exactly the same thing. And yeah, so that's okay, cool. So that's chapter 4. I could explain more, but it's just gonna be repeating yesterday's from chapter 16, but it's the same thing, 4, 5, and 6. But if you want more great detail, it's this. And the way they could be asked is, again, it's very intuitive. You have to understand the tree data structure and all. So okay. So yeah, that is like, do you guys still have any questions about 4 or 5 or 6? Or like want me to go more in depth? Because I don't think there's much more else to cover other than like what I already did. Mm, waiting for yeah, it's cool. So yeah, like if you guys want more, if you want me to cover like talk about another chapter, if you need help with anything specifically or like an exam paper question, I would suggest just practicing. At least you can ask, either post a question or like come to me directly, or that I will try to help you out as best I can. But the resources are here, chapter 8, chapter 6 and 9. At least this is the only video for chapter 6 and 9. But I'd say this practically gives you enough to get started with compiler, write down notes in your notebook, and yeah, so it's nothing particularly too. The module isn't too difficult or such. Just the content is like it takes a while. Just take some practice, check if you're wrong, and be able to check if you did something wrong. Because the most annoying thing about the module is that it's like you, you'd have to spend 30 minutes just doing converting an NFA to a DFA. But the more you do it, the faster you get and the more confident you are. Yeah. Um, if there's anything else anybody wants me to cover in particular, let me know. Uh, if not, we can end the session right here. And so, yeah, sure. Yeah. Chapter 2.
Hello, sorry, I'm just gonna unmute my mic and type all this.
Yeah, no problem.
You mentioned in
Hmm.
just at the end of chapter 2 that it's easy to prove the ambiguity and to find errors. Is
Yeah.
there any examples on the videos you made or in the
Uh,
textbook on that?
to prove ambiguity, right?
Because I remember in the exam that
Mhm.
one of the questions was to prove ambiguity. I think I struggled with that quite a bit.
Oh, okay, not a problem. So I do have a video that does explain that, but I can explain it right now. Um,
But if you explained it in the video, I'm sure it's fine.
yeah, it's just fine, but it's fairly simple. So it's in the chapter. Let's see, chapter 1 over here, and written. Is it wait? Chapter 1 ambiguity. No, chapter 2. It's this one over here. They don't overlap. So it's in this. I think it's the first. So the first 15 minutes. So with the newer videos, this. I tried to give some context, at least like try to explain the chapter before starting. And for this one, I do explain what ambiguity is and like
hello.
I do left recursion and pausing and left factoring and how to prove ambiguous grammar and such and how to eliminate it.
Thank
And
you. I'm sure that'll be good enough.
that should be good enough. But yeah, if you can
Good.
come up with one syntax tree, you're good. Okay, is that all? Does anyone else have a question? I'm free for like anything else as well. But if you okay, okay, goes typing. Any basic advice? I would say okay, I'm assuming that your notebooks, you're still allowed to carry your notebooks into the exam. So cool. So for that, I would suggest doing all of your practices like on the notebook, like all of your exercises, so that you have something to refer to as well. For each chapter, let me just give some advice for like each chapter, at least the best way to go about it. So for chapter one, knowing how to translate from a regular expression. So I'm just gonna write regex from regular expression to an NFA to a DFA and to a min DFA. I do explain how to do that in one of the videos. Um, you can use any method, like you can convert an NFA, a regular expression to NFA. The textbook does explain how to do it, so that the textbook method is like the fastest way. Or the fastest way is like intuition, where you can convert you can use any technique to convert a regular expression into an NFA. The textbook does use the idea of segments, which I do go over, but you can, if you already know regular expression from programming, you can just directly like convert a DFA, a regular expression, into an NFA. For example, if you have something like this, like A star, uh, B, C, plus. I think the plus means at least one C followed by any number of A's followed by a B. So you can just like in general, just let's see, have one C followed by, let's see. Okay, if you have the C over here, you can just draw the DFA straight from your head. In my opinion, at least let me try to do that over here. You have C, you can have like the C over here, then followed by an A, uh, yeah, followed by an A, but we don't have to have any A's over here, so we can have like a B. Since B is the last one, it's gonna be like this. So we can have A, any number of A's, like that, and like that if you have a B. So this is how you would like describe these. Let me just erase. You can so you can use the textbook from the method, or you can just do it straight from your head if you have like an intuitive understanding of this. This is very useful, at least if you want to do it fast. I'm very slow because I've not done this a lot, but the more you do it, the faster you do. And that way, my point is that when you're converting from regular expression to NFA, you can use any method as long as your NFA makes sense. It follows the same logic. So it could look much different. Like if, it could be different, or mine doesn't have any. See, this just you just have to follow B as well. And when you're converting from NFA to DFA, follow the method I mentioned. Uh, this one over here, and you'll be practicing for both chapter one and chapter two. So you get a 2-for-1 special over there. And DFA to min DFA. Um, there's only one way you can do this, at least as far as I know. So you just keep practicing that. And yeah, that so once you understand this whole flow, chapter one questions become like very easy to do. And chapter two, I think in my video I do a good job of trying to explain, at least separating these three algorithms, because each one has its own that yeah each algorithm here has its own has its own this. So having this in your book explaining it will help a lot, and also having like little notes as well and examples. So there is one for LL1 that explains it like for LL1 in the textbook. So having that in your textbook will, pretty sure will help so that you can like have something to look back on. And once you like understand these, uh, in my chapter 2 video, I do explain like again intuitively. Like I explain chapter 1 here, then I explain chapter 2 here as well. You can try to skip ahead where I explained the SLR pausing. So I do explain some tips there and how to do some things faster. And in the video, there are parts where I just have little notes. But I was doing a bit of editing. So that's just chapter 2. It's fairly simple. It's either you're making a table or you're going to pause with it, or you're going to do something with it. And it's fairly simple. So, but it just requires some practice. And 4, 5, and 6, they're the same chapter. The difference is the goal, evaluation, correctness, and translation. And the main differences will be the V tables and the F tables. They might have different information. So, like interpretation, the F table might have an actual function that might do something, or at least the function names. And vtable define the variable values, and the correctness, it checks if the what the types of the variables are and the return types of the functions are, and the translation. So what I'd suggest is going through the tables, try to understand them and try to understand them programmatically as well. So if you're able to code them like because again it's no different from 212, at least from when I did 212. Like it's kind of like a programming problem. And if you're able to write it like using C++ or anything really, it becomes easier to understand. So that's just 4, 5, and 6. They're all asked the same way. Chapter 7, I did not do chapter 7. I think chapter 7 is like direct translation where if you see something like there's nothing clever about it in my opinion. Like this is the whole this here is literally the whole point of chapter 7. Right? If you see this, replace it with this. And the exam question I've seen on chapter 7 is usually just like it's usually it's a question that I don't even think you need to study for. It's like I'm not saying don't study chapter 7, but the questions are usually the last questions I've seen is like so simple, like translate the following sentence. Like see, like let's see, hello you, and you have to translate to Japanese. You just see like you translate the word directly, hello to its direct counterpart, and you to Chinese as well or whatever. So it's yeah, there's not much about this chapter that's like really special. So usually it's glossed over, but it's just direct mapping or like pattern matching and just replacing that. So there's that. Chapter 8, I have a video on that as well. I explain the whole process. It takes a while. There is a way to do it really fast that I explain over here in in this section over here, how to do chapter 8 very fast. It's just you normally the textbook does like show you like the tables. You don't have to rewrite the iterations. You can just write two columns in and out, and just do the first iteration on like the first table is the first two columns, and then reuse the column so that you don't have to recalculate the same thing instead of like because if you look very closely, you'll notice that like nothing really changes when you go from here to here to here. It's only like these two things that get added, and then nothing changes as well. So that's like chapter 8. You can do that like fairly quick, but the whole chapter is fairly simple. Chapter 9, Chapter 9 is just a continuation. It's usually asked with chapter 6. And it's as I explained yesterday. If my explanation from yesterday is confusing, I wish I could like show you again, but I would suggest using Excel to like simulate using Excel to like simulate the stack and have the stack pointer and then look at the translations where when you're like um so yeah, using Excel or like Google Sheets to simulate the stack, and then you're looking at the translations, the caller save and callee save prologue and epilogue, and you'll notice that when they do these calculations, when they do these calculations over here, you'll see that the way it's moving, it's like there's logic to it, and you'll be able to like see it intuitively as well. But chapter 9 isn't too difficult as long as it like yesterday's explanation made sense. But yeah, that's like the general for each chapter. But if I were to like give overview, like a general advice, like for everything is just to have notes. Do your practice exercises on your notebook so that you have something to refer back to as well. And yeah, and also be able to check if you did something wrong, which you can only do if you do practice as well. And yeah, that's pretty much it as well. I'm still open to like questions. Like you can still message me if there's like anything direct as well. And some of you emailed me, and I did give a much more detailed explanation for each chapter. Yeah. Yeah, that's like a mouthful, but hopefully that helps in some way. Huh? All right. So yeah, I believe in you guys. I know it's like might be a bit overwhelming, but I'm pretty sure you got it, and it's I'm pretty sure you guys will do well. This is my second boot camp, and I think the last one is a lot. It's a shame that all my old videos got deleted because